All right, so today what I'm going to talk about is another result, sort of in the lines of importance sampling. It's not one that is sort of commonly taught in a randomized algorithms course. It's a much more recent result, but it's actually a fantastic result and extremely practically viable. So I'd like to tell you about a result about by Cohen and Lewis, and this is fairly recent. This is actually 1999. And so this is an approximate uh, matrix multiplication result. I should say that, sort of the presentation of Cohen-Lewis is, although it's basically the same element, this is sort of my presentation. It's my take on it, which is slightly different from the way that it would be written in the paper. So let me actually begin by giving you a motivating example, actually one that comes up in practice quite a lot. And so we are given sets S1, S2 up to Sn over D elements. So you have a collection of sets, and so you can think of each of the Si is basically some subset of the universe of D elements. And I say find all pairs of sets with large intersection. And of course, I haven't actually told you what I mean by large, but maybe I could say that suppose typically intersections are quite small. Let's say are O of 1, and I also said all pairs, right? I want pairs with intersection maybe more than some. So obviously the maximum intersection would be D, would be maybe something like D to the delta. Maybe I want D to the 1/3, something. It doesn't matter. It's some parameter. So you could think of this as I'm going to put something like K over here, where K is going to be much, much larger than the typical intersection. So this comes up a lot in, under the hood in many places in machine learning when you're actually trying to get, extract features and do similarity. You will often maybe represent your object as some kind of, let's say a categorical vector, and then and maybe this would be your interests. So for each person, the D elements would maybe represent different interests, and in this case the interests would just be Boolean, and so each person, which is one of these sets, has a collection of interests that they are interested in, and we're trying to find all pairs, so all pairs of people who share lots of interests. And we typically might use this somewhere down in like a recommendation system. And I'll give you actually the specific example that I have worked on relatively recently. This was a few years ago when I was doing some similarity work at Twitter, where where maybe what you want, we want large cosine similarity. So what is the cosine similarity of two sets? So it's some kind of normalized version of the intersection. It's that. Really, the way to think of this is that you look at each SI, you can think of it as a vector in 0, 1 to the D. So it's got zeros, ones, zeros, so on and so forth. What I could do is normalize. So the vector has unit to norm. So what that means is the normalized version, which I'll refer to as VI, would essentially have 1 over root SI wherever there's a 1 and zeros otherwise. So on and so forth. And then the cosine similarity. The cosine similarity is really just the dot product of the corresponding vectors, right? So these vectors, they're not Boolean, but they essentially, all the non-zero entries of an individual vector are the same, and then you take dot products to measure similarity, and then you could ask for, give me all pairs of vertices. In this case, it would be users who have a large cosine similarity. And so the maximum value of cosine similarity is 1. So the cosine similarity is at most 1. And of course, in this case, these are all non-negative vectors. So, it's basically between 0 and 1. And typically, you're trying to find everything, all pairs, whose cosine similarity is sufficiently large. So does the problem make sense? Okay. So now let's start. Let's begin with again how one would do this in practice. So let's just try to do it exactly. Let's solve exactly. So sort of the brute force solution, brute force is to sort of enumerate over all pairs, and so let us start with and compute the intersection or the cosine similarity. Just you can get, for all pairs, you can just compute. And so this, no matter what sort of you did over here, obviously this is definitely going to be omega n squared, right? Because you're enumerating over all pairs. And a typical application to think about is like maybe n is 1,000,000 or even more than 1,000,000. This is already sort of, this is out of bounds. This is not going to be efficient. And if you were to, instead of 1,000,000, you were to make it 10 or 100 times that, then obviously this is just completely infeasible. So often what we observe in data of this form is what I'll call sparsity. So what I mean by sparsity is that on the average, let's say the size of SI is going to be relatively small. Okay, so on the average SI is small, which means it's much smaller than D. Okay, so SI is going to be small. It's much smaller than D. And so, can we exploit this property for solving this problem? And so what you might observe is, I actually said this is approximate matrix multiplication. So we can pose this directly as a matrix multiplication problem. So let us restate the problem in terms of matrix multiplication. In terms of matrix multiplication. So I'm going to write out these vectors here. So you can think of these vectors as either SI or vi basically written as a vector in r plus to the d. Now this plus is going to be important. So these are all non-negative vectors. Okay, so this is d, this is n. I've drawn this as a rectangular matrix, but you could probably assume that d might be quite large. Okay, so d could be large. And in many applications, d might even be equal to n. Okay, that's not an uncommon setting. So I'm going to refer to this matrix as A. Okay. So what am I looking for? I'm looking for all pairs of columns whose dot product is large. Okay. Oh, and by the way, before I continue, I said sparsity. Remember, I mentioned sparsity means that I'm going to use this term called the n and z of A. This is the number of non-zeros. The number of non-zeros in A. So the sparsity of A you can think of as, as typically like O of n, or it's some constant times n. It's some, let's just say, I will call it, maybe I'll call it, k times n, where k is typically much smaller than n. Right? It's extremely small, not even less than n. It's more like O of 1. Okay, so this is sparsity. So let me look at the Gram matrix, or the Gramian matrix. The Gram matrix in this case is A transpose A. Right? So what is A transpose A? So let's sort of write that out. So this is A over here, and this is A transpose over here. So in A transpose, all the vectors are rows. In A, all the vectors are columns. And so if you look at A transpose A, so remember this is n, this is d, and this is d, and this is n. So if you look at this matrix, you get an n cross n matrix. So you get an n cross n matrix. Sorry, just a second. Something got disconnected here. Okay. Sorry, can everyone see everything now? Everyone can see in here? Yeah. Okay. So, so this is the matrix A transpose A. And what you have in A transpose A is the ijth entry. So what is the ijth entry? So let's refer to these column vectors as vi. Right? What is the ijth entry of the Gram matrix? Exactly, right? So it's just vi dot vj. So the Gram matrix is the matrix of dot products. This is the matrix of dot products. And so if I can rephrase the problem by saying that given vectors v1, v2 to vn in r plus to the d, so these could either be Boolean vectors, or they might be these normalized vectors, or there could just be arbitrary vectors at this point. Let me sort of state it more generally. I said the problem was to find all pairs I comma j where vi dot vj is large, which is equivalent to saying find all large entries in the dot product in the Gramian matrix. Right? So that's what it is. So far, of course, there's no randomness, no randomized algorithms. But it's right. So I could, so let's start. So the exact algorithm just computes A transpose A. And so for this, let me revisit the sparse matrix multiplication algorithm. The sparse matrix multiplication. The sparse matrix multiplication algorithm. So remember, I had a matrix A, and so I'm going to sort of use some notation over here. I'm going to introduce some notation. Let me use, so of course, this is for any R and I. So this is A R I. So remember, this is a dimension. That is the index of a vector, right? Because these are the column vectors we're looking at. So this is ARI is the rth entry of the ith vector, right? The rth entry of the ith vector. So instead of vi, let me refer to this vector as A star I, where star just means it goes over all possibilities, right? So A star I is this vector here. This is A star I. Okay. So I'm introducing this notation. I'm going to come back to it shortly. So I'm going to describe sparse matrix multiplication, and the easiest way is to picturize this in terms of a graph. So I'm going to create a tripartite graph. A tripartite graph representing the matrix product. A transpose A. So how is this going to work? I'm going to create a tripartite graph. So here, these are labeled with indices. So index is an element in n. So there are n vectors. This is an index. This is a dimension. That is in D. And this is an index in n. So you should think of this as an index, which is just an index of this, and this is again an index of that. It's the same thing. And now what I'm going to do is I'm going to create a graph here. So for any index I and a dimension R, I put the weight of this as A R I. And similarly, for any index j over here and a dimension, this is going to be A R j. So this is a weighted graph, right? So a weighted graph, a weighted tripartite graph. Okay, does this make sense? Okay.
Can you explain the construction once more? Sorry.
Sure. So remember, I started with a matrix A, right? So matrix A, this was D dimensions, and this was n. Remember, so I'm thinking of this matrix as n vectors in D-dimensional space. So I have sort of two, when I'm indexing a matrix, right? I have an index over here and an index over here. So for convenience, let me use index for this, and let me just say this is a dimension because there are D dimensions. So I'm going to use generically R as a dimension, and I'm going to use I and j as indices. So R is an index of a row, and I and j are indices of columns. Now my tripartite graph is going to have three sets, right? So there's an index set, a dimension set and an index set. So in this case, the index set is there are n indices here. The dimension, there are d dimensions. So this is just simply, this is just a set of n vertices labeled 1 to n. This is a set of d vertices labeled 1 to d, and this is again a set of n vertices labeled 1 to n. Okay? Now I'm going to construct, so this is my vertex set. Now I'm going to construct edges between the indices and the dimensions. Right? So there's an edge from here to here, and there are edges from here to here. So for every I and every r, so r is a dimension, I is an index, the weight of that edge is a sub ri. Right? So if you want to look at the entire vector, I'm sorry. So if you fix your I and you look at all the edges that are going out of I, this kind of represents the vector vi, or it represents a column, right? Because for every entry here, as you're changing your neighbor, you're changing the dimension. Whereas on the other hand, if you look at this, so fix a dimension and look at all the indices, you look at this is a row vector. This is the row. And this is an n-dimensional vector. This is an d-dimensional vector. Right? So, and what I'm doing here is I'm just duplicating this picture on the other side. So for every dimension and every index, the weight is just the corresponding entry. Okay? Does that make sense?
Yeah, thank you.
Okay. Now let's look at a path. And by path, I always mean paths that go from here to here to here. Okay? So this is my path of length 2. From index to a dimension to an index. Let me look at a path of length 2. So a path of length 2 would go from I to R to J in this way. And let me say the weight of the path is just the product of entries. I'm sorry, it's ARI, ARJ. So this is the product of entries. The product of weights. Right? The weight of a path is the product of the weights. Okay? Now, how would you represent an entry of the gram matrix? So let's look at the gram matrix, right? So remember, this is the gram matrix here, which is really what I'm trying to compute. What is the ijth entry in the gram matrix? Can you relate it to some weight or to some paths over here?
It's the sum of all the weights of the paths that start at I and end at J.
Exactly, right? So what is vi dot vj, which is the same thing as A transpose A of ij. This is the sum of weights of paths starting at I and ending at J. Right? Why is that? Because if you look at, okay, so let's go back to this tripartite graph. Let's fix an I over here and fix a J over here. Every path goes through some R. Right? That's what all the paths look like, that go from I to J. So you're summing over all R and D of the weight of the path, I going to R going to J. With this, as we discussed, we know that the weight is ARI, ARJ, right, which is precisely the dot product which is just the dot product of these vectors, which, again, as I said, I'm going to write A star I dot A star j. Right? There's a dot product there. So these are vectors. Right? So A star I dot A star j, which is exactly what I'm looking for. This is the gram matrix, or you can also think of this as vi dot vj, right? Because I said this is exactly vi and this is vj. So this is the dot product of two of the columns. Okay, does this make sense? Any questions on this? Okay. So this is actually, and if you look at this algorithm, this is really the state of the art sparse matrix multiplication algorithm. By sparse, what I mean is the number of edges in here is much smaller than n times d. If it's dense, then it would be n times d. So sparse matrix is that the number of edges here is much smaller than n times d. Okay? So let's revisit. So what is the total running time of the algorithm? So what is the algorithm? Maybe I should tell you what the algorithm is. The algorithm would be, construct tripartite graph, compute weights of all paths, and then sort of sum appropriately to get all entries of A transpose A. So what is the total running time? I mean, it's going to be hard to write out analytically, but just sort of intuitively looking at this, where's the bottleneck? What is the part that you think is going to be the most expensive step?
Constructing graph. There aren't going to be that many paths, but I guess then maybe.
So which is the expensive part?
Is it computing the weights of all the paths?
It's computing the weights of all the paths. How long does it take to construct the tripartite graph? It would be nd in the worst case, but suppose I told you, remember we were discussing that in real world data, the number of non-zeros is actually quite small. So nd would be in the worst case. That is exactly true. But in general, the sparsity is quite small. So given that the sparsity is small, surely you can construct this in time O of the number of non-zeros of A. Right? Do you see? I mean, basically, you literally have, this is giving you the adjacency list representation. Right? Okay, so now there are some questions as to how exactly have you stored the matrix. But if you store the matrix as an adjacency list, so this is n z A, and assume A is stored as an adjacency list. Remember, this is fundamental. So this is, if you think about a lot of machine learning applications, and in machine learning applications you will have millions to billions of items with potentially millions to billions of features. If the graph was dense, there would be no hope of storing these graphs. They're typically sparse, which means that you can store this in NNZ-A storage rather than n times d storage.
Sure.
Does this make sense?
Yeah.
And so you can construct the tripartite graph in time n and z of a. Right? But to compute the weights of all paths, this is obviously, at the very least, this is going to be O of the number of paths. Right? This is at least the number of paths. So the total running time one can write as the number of non-zeros in the matrix plus the number of paths of length 2. Okay, so let's investigate what this quantity is. Okay. So let's go back to the matrix now. Let's go back to the tripartite graph. Okay. And remember, so there are all these paths that are going through the graph. Now let me look at every vertex in the middle. Let me look at every vertex in the middle. Remember, these degrees are the same, right? Because they're exactly, this is, these, you know, this graph and this graph are essentially identical. They're just one is mirroring the other. So the total number of paths of length 2 is equal to the sum over all R and D over the degree of R squared. I mean, okay, it's like half. You know, you could think of one of these being the degree. So it's the degree, either, you know, you could just say, I'm just doing O. Does this make sense? So you basically square the degree. Right? And this is O of, it's the support of, okay, so now let's remember what I said was this represents a row, not a column. This represents a row vector, not a column vector. This represents a column vector. This part represents a row vector. And so what is the support? You're looking at every dimension. You're looking at the support and squaring the support. So this is the support of AR star squared. Remember, so now what I'm doing is I'm fixing a dimension and going over the entry. So this is the number of paths of length 2. Okay? Does this make sense?
Yeah.
And if A is Boolean, which is the first application we talked about, then AR star, you know, the support is the same as the one norm. Right, so if A is Boolean, then the total running time is, it's O of n and z of A. So we'll think of this as something like, this is like O of n plus the sum over all R in D. Remember, if this is Boolean, then I can just write this as the one norm squared. Now, as an exercise, this is not, you know, you can see this yourself. You can write this. This turns out to be exactly equal to all ij of the dot product of A star I and A star j. So this is like, you have to write it out as a summation. You expand things out, and what you get is, if A is Boolean, the total running time is the number of non-zeros plus the sum of all dot products. Plus the sum of all dot products. Now, this quantity here is typically much, much smaller than n squared because most dot products are 0. Most dot products are 0 when A is sparse. Which kind of makes sense, right? When A is sparse, most of the vectors that you're looking at have constant support, and therefore they will only intersect with with a relatively small number of sets. So this is the total runtime for exact matrix multiplication. And so I'm going to write this out in somewhat of a more convenient form for me, which is, I'm going to get this O of n and z of A plus what I get is this is A transpose A. Okay, I'm going to use a norm notation here, but what I simply mean is this is just the sum of absolute value of entries. I'm just sort of treating the matrix as a vector. And this, again, under most normal circumstances will dominate this. So this is when A is Boolean. And when it's not Boolean, then of course this has to be a zero norm, it has to be a support, which is different. But when this is Boolean, then this is exactly the amount of time required to compute your dot product exactly. Okay? So this is exactly the time that it takes. This is the time. Okay, so any questions about that?
Sorry, I missed this. AR0 is equal to AR1.
This part. So I'm just so I'm looking at the support of the vector, right? The zero norm is the support. So if it's Boolean, the number of non-zero entries in the vector is just the sum of entries, right? Because any non-zero entry is 1. So that's all I'm saying here.
Thanks.
So any
Can you explain? Sorry.
Yeah, go ahead.
Sorry, I think I missed the definition of the support.
Oh, the support is the number of non-zeros in this. So another way to put this is go back to this tripartite representation, right? So there are only some edges that have non-zero weight, and those are exactly the non-zero entries in that row vector. Right, so let me show you that picture again. So the neighborhood of this vertex is a representation of that vector. The neighborhood is a representation of that vector. The number of non-zeros in the neighborhood is exactly the number of neighbors of R. And so the support, that would be the support, which is just the number of non-zeros.
And then I guess here, so the path from I to D and then going back to the same I will also be counted here.
That's true. That's a good observation. So the paths, which is essentially like it's the self dot product, right? Which is in the self dot product would be the 2 norm. So we are typically trying to find all pairs with large intersection, and we may represent sort of the set with itself, but we can always filter that out later. But you're right, like that will also appear in this. Because at this point I'm basically just doing an exact matrix multiplication. So this, I mean, ignoring randomized algorithms, what I have described to you is pretty much the state-of-the-art matrix multiplication algorithm as you would do it in MATLAB for sparse matrices. This works for sparse matrices. And indeed, this representation of a sparse matrix as an adjacency list is useful because you can start doing these computations rapidly. Okay, so far so good. Okay. Now, again, I should stress that this is not exactly either the application or the exact presentation of Cohen-Lewis's algorithm, but indeed it's basically its equivalent. And so one question one can ask is, let's go back. So I'm going to sort of switch between the Boolean view and the real world view. So the algorithm description I will do in terms of the more general view in which V is just a collection of non-negative vectors. On the other hand, I want you to sort of keep the Boolean case in mind in terms of analysis of the running time. So let's go back to this application of S. Yes?
I guess I have one question, which is like when we're analyzing the running time, it seems like the number of edges, like there's two sets of edges, like the left hand side and the right hand side, and they're both the same.
That's correct.
Like, the number of edges is exactly the number of non-zero entries made, right?
The number of edges is exactly the number of non-zero entries. You're right.
So can we just say that the running time is like so the number of paths is like the square of the number of non-zero entries?
Yeah, but the thing is, it's, instead of doing the number of non-zeros in the entire matrix, you're summing it row by row. So this is going to be smaller.
Oh, sure.
So this is a sharper bound. But it's significantly sharper because if you just took the total number of non-zeros, you'd get a bound of n squared here at least. And I'm saying this is going to be much smaller than n squared. This is much smaller than n squared. I mean, it's much smaller. Okay, let me be precise. It's smaller than n squared. When you look at real data, this will be much smaller. Yeah. So let's go back to this application, S1, S2, up to Sn. And let me say, I'd say find all find all pairs whose intersection is large. And so we said like a baseline running time. So sort of, let's say the bad baseline running time. This would just be something like O of n squared times d. Just brute force everything. Right? And or at the worst case, whatever baseline we come up with, even if you could improve this somewhat, you're looking at O of n squared. Now the better baseline, we said in this case, was this one norm, which if you think of it is really just saying it's the sum of all intersections. Right? That's the better baseline. Now this, of course, finds all intersections. So it's doing much more than what you want. Not just large intersections. So what Cohen-Lewis asked, can we beat this bound? Can we beat this trivial bound for finding large intersections? For large intersections. And what they did was they basically built an importance sampler. So the main theorem of Cohen-Lewis is that in O of number of non-zeros of a plus n plus d time, we can build a data structure, a randomized data structure, that outputs. So what I mean by randomized data structure, it'll be clearer when I make the description, but the way to think of this is that it's this black box that we're going to build. It's a randomized data structure. You press a button, this is going to flip some coins, so it's going to flip coins, and then it's going to spit out a pair I comma j. So it is going to output I comma j proportional to vi dot vj, or using our other notation, it would be a star I dot a star j. And it outputs this basically in O of 1 time. So in essentially linear time in the input size, I'm going to build a data structure. It's a randomized data structure. Now when I push a button, this is going to flip coins, and it is going to output I comma j proportional to vi dot vj, or proportional to a star I dot a star j. I assume that A is a matrix in R plus d cross n. So what is going to be important is that it is a non-negative matrix. So this is the theorem statement. This is what Cohen-Lewis proved. Now using this, we can see that, going back to our our friends of using binomial tails and Chernoff bounds, we'll be able to analyze how long it takes to find all large entries. But first, what I want to tell you is how to build this randomized data structure. Okay? And essentially, the data structure that is built is exactly this. It's exactly, you build the tripartite graph that we described, and the idea is simply sample a path I going to R going to J proportional to its weight. So you're going to sample a path proportional to its weight, and so then the probability that ij is output will exactly be proportional. So that's not alpha, but rather the proportionality symbol. This is going to be proportional to a star I dot a star j. Okay, so let me describe the algorithm. Let me describe the sampler. So the Cohen-Lewis sampler. So the first thing we're going to do, we're going to pick R, which is a dimension. Remember, R was a dimension with probability. Okay, so let me write this out and then I will describe it. Okay. So what am I doing? So remember, I want you to keep, in some sense, you're going to have to keep 3 pictures in your head. One picture is just the original matrix. One picture is the tripartite graph. And the third, not picture, but rather algorithm, are these numbers. So the first thing I'm going to do is I'm going to pick a vertex in the middle. A vertex in the middle, which is equivalent to picking a row in the matrix. Now I pick it proportional to a seemingly funny quantity, which is I look at the L1 norm of this row matrix. I look at the square of it and I pick it proportional to that square. Okay, pick it proportional to the square of the L1 norm of a row. So I first pick an R. I pick R. The second step is now I pick I with probability AIR divided by A star R1, which means from R, I look at the neighbors and then I'm going to basically flip some coins. I'm going to pick an I. Then I pick J with probability AJR. Have I mixed up my coordinates? I think I should be, my apologies. Oh dear. So it should be R, I mixed up my indexing. It should be R star. Okay, this is, sorry. This should be A R star divided by the sum of A R star, R going from 1 to D.
So, to be clear, we're assuming that A has entries in R plus, right?
Exactly.
So
yes, so these,
one norm is just the sum.
yes, the one norm is just the sum. Okay, so sorry, I mixed up my indices, so just let me just rewrite this. Let me just rewrite this. So the CR sampler is first I pick R in D with probability A R star 1 norm squared divided by A R star 1 norm squared, summing over all R and D. Right? So that's basically the equivalent of picking a middle vertex in the tripartite graph, which is the same as picking a row. Then I pick in an I in N with probability ARI divided by the sum of entries over here.
Sorry, for the first step, is it necessary to use square?
Yes. It's a good question. Why do I need to use the square? And you'll see the square when I do the analysis. You have to do it with the square. You cannot do it with just the one norm. These are sort of very carefully cooked up. So I very carefully cook these things up so that everything will work out to be unbiased. Okay, so then I pick J with this. Okay? Alright, so to build the data structure, so this is the sampler. So the pre-processing step is to simply, set up or construct data structures to allow such sampling. We only need to compute these row sums, right? So one has to compute this for all R in D. Okay, this is linear time, and then set up these data structures and set up. So we set up essentially D plus 1 sampling, D plus 1 distributions to sample from. Okay, so what are the D plus 1 distributions? First, you have to set up this distribution. Then, for each R, you have to set up this distribution. Right? So first, you have a distribution to pick R. That's this one. That's picking it proportional to the row norm, the row 1 norm squared. Then, for each vertex in the middle, you need a sampler to sample from the left and sample from the right. In this case, it's identical. Now it turns out, and I'll get to this shortly, is that you don't need to assume that they're identical. You can actually do this even when you have not A transpose A but A transpose B. But we'll come to that We'll come to that later, right? So you need to set up these distributions. So you need to set up these D plus 1 distributions to sample from, and this is an exercise. But the total storage is just going to be O of n and z of A, plus n plus d, which is really is just this. And I'm just putting this to be formally correct. Okay, does this make sense? So this is the pre-processing. Any questions? Okay. So now let's do the analysis. Let's do the analysis of the sampler itself. So the analysis.
Sorry, why is it d plus 1 distribution?
So you have one distribution for each vertex, right? That's what you're sampling from here. But then you also have this one distribution at the beginning. Remember, this is a distribution that is sort of global, right? This is just to pick a vertex. And then you have one distribution per vertex in the middle. So it's d plus 1. So what is the analysis of the sampler? So let's just, and so the claim is the probability that I comma j is sampled. We'll see that this is going to be exactly equal to A, let me make sure I get my indexing correct, A star I dot A star j. Remember, so A star I and A star j are looking at columns. This is looking at columns, divided by the one norm, the sum of all these entries, right? So this is essentially a probability distribution. Is the probability of sampling I and j is proportional to the dot product of the corresponding vectors, or remember we call this vi dot vj, right? It's the same thing, divided by the one norm. Okay, and so the proof of this is, it's quite simple. So let me just break this up into conditional events. So what is the probability that ij is sampled? Well, it's the summation over all r and d of the probability that ij is sampled conditioned on r being sampled times the probability that r is sampled. Right? So I just broke up this probability into a bunch of conditionals, and those conditionals are exactly according to what is the middle vertex. So another way to think of this is I know that I and j have been sampled, so there must have been some middle vertex that was sampled. So I go over all the middle vertices, and for each vertex I first say what is the probability I sample this vertex? Conditioned on sampling this, then what is the probability that I sampled this path? Then I go to this vertex, say conditioned on this being sampled, what is the sample of that? So probability of sampling this path, so on and so forth. Does this make sense? Any questions? Okay. So let me just sort of keep this expression over here. And so now it's just a matter of cranking out the expressions, the probability that ij is sampled. Okay, so first, what is the probability? Now this is these are independent, right? So this is now the probability that I is sampled conditioned on r is sampled times the probability that j is sampled conditioned on r is sampled times the probability that r is sampled. And that's because I should have said probably independently. This is all independent randomness, independent, independent. Right? This is all independent sampling. So I fixed R, I picked I independent, J and I independently and J independently. Okay. All right. So now what are these quantities? So what is the probability that I is sampled conditioned on R being sampled? Let's go back, look at the expressions. So what is the probability that I is sampled?
ARI over 1 over AR star.
Exactly. So it's ARI times AR star 1 norm. Probability that J is sampled, ARJ divided by AR star 1 norm. What is the probability that R is sampled? It's right there. AR1 star divided by the sum of these entries. And now do you see that this cancels out with that? And for the question as to why we use the square, we use the square exactly so that we could cancel this out. This is a constant that is independent of R, so this is going to come out. So you have 1 over sum of the R of AR star 2 norm. You have R and D, ARI times ARJ. What is this quantity? What's that?
It's the number of dot products.
Sorry?
It's the number of two paths, which is the dot product.
It is the dot product, right? This is exactly the, or rather it's technically the weight of the paths, which is the dot product. So I got exactly what I wanted, which is I got A star I dot A star J divided by this which I said, I sort of mentioned before as an exercise. These two are the same thing. This is an exercise. It's just a matter of summing it differently, and so you get exactly what you want. It's beautifully simple, right? So in linear time, you set up this data structure, and you can sample exactly. You get an importance sampler. Okay. Any questions?
Is the square in the sampling of R merely to just make it convenient? Is there any other intuition? Because it seems kind of odd to me.
Say that again. You mean to have the square in the sampling?
Yeah.
The square in the sampling is, yeah, in some sense, that's the smart bit. That's exactly there to cancel these factors out so that you get the dot product. So you can think of it as, right, this is sort of setting things up so that your importance sampler works as behaved. So this feature of sort of, or I should say this aspect of sort of computing these very carefully constructed distributions is a theme that appears over and over in randomized algorithms. Like similarly in Karp-Luby, like you had this sort of, you had to sort of sample things in a particular way and write out the correct random variables. Once you write them out, the analysis turns out to be, at least the expectation analysis turns out to be fairly straightforward. It's coming up with these expressions that's usually that's the hard part. Okay, so far, okay, again, now I have told you how to do the importance sampling. So what we have just discussed is the main theorem statement of Cohen-Lewis, which let me just sort of pull that out. Wanted to sort of, there it is. So we have argued that in NNZ, this is the time to build the data structures. We build a randomized data structure that outputs ij proportional to vi dot vj in O of 1 time. So this is something that I will talk about maybe in the last 10 minutes, but you notice that there are only 3 steps here. Right? So as long as you can sample from a distribution in O of 1 time, you can do all of this in O of 1. So it's constant time to get a single sample. Okay? So any questions about this theorem, or I'm going to, if once, if as long as this is now clear to everyone, then I can continue with the next analysis, which is really now how we're going to find all the intersections that are large. That's a good question. So, but if you think about it, you can just store the distributions as a list of numbers.
Okay. Oh, and then you just yeah.
I mean, the most naive way to do the sampling is you store these numbers, you store partial sums, and then you do binary search.
Okay.
Then you get log n per sampling, and then I'll show you how you can improve that to get O of 1.
Okay.
But let's, abstracting that aside, hopefully this is clear. We now have built our importance sampler. Now that we have the importance sampler, we now need to actually find all pairs whose intersection is large. So any further questions on this theorem? All right. Then let's continue. Now we're going to start doing our favorite coin flipping type analysis. So now let's say we want all intersections at least k. Okay, we want all intersections that are at least k. So fix some ij such that Si intersection Sj is greater than k. What is the probability that ij is sampled? What is the probability that ij is sampled by the Cohen-Lewis sampler, by the CL sampler?
It's the size of the intersection divided by the sum of the sizes of all the intersections.
That's right. And so we said the size of the intersection is at least k, right? I fixed some ij. So this is at least k divided by A transpose A, right? This is what we argued. Remember, I said that the baseline algorithm is going to be essentially A transpose A 1 norm, and I want to beat this baseline. So the probability that ij is sampled is at least this. So how many samples required to sample or to get I comma j? How many samples do I need? Give me an upper bound. So this is the probability. Now let's think of it as coin flipping. This is the heads probability. This is your probability of success. How many trials do you need to see a success?
Order of n.
Order of?
Because the number of non-zeros is equal to if the number of non-zeros is O of n, right?
The number of non-zeros is O of n, right? But this is the probability that ij got sampled,
Oh, okay.
right? So
Call that P just 1 over P epsilon squared.
it's 1 over p epsilon squared. So if you call this p, it would be 1 over. So okay, now you're right. So it's 1 over p epsilon squared. Although you need the epsilon to get an approximation to the quantity. For now, let's just say that the probability to just get it, that's how many samples I need, with some O. And you're right that you need a 1 over epsilon squared. If you wanted to, let's come to the 1 over epsilon squared shortly. That's how many samples you need to just get it. What is the number of samples you need to get this with probability at least 1 minus delta?
Just log 1 over delta.
you just multiply this by log 1 over delta. Right? That's how many samples you need. So this was your trivial bound, and you're beating that by a factor of k. But I haven't finished the analysis. This was only the analysis to get a single ij. We wanted to get everything. We wanted to get everything. Okay, now we have to be a little careful, and we are now going to do an extremely common and powerful argument, which is the concentration plus union bound. Very, very common and powerful argument. So what we said is the number of samples to get a specific pair is this much. How many pairs are there? Now the problem is there could be many pairs, and you want to get all of them simultaneously. So we said the probability of getting ij with these many samples is at least this. What we want is the probability of the intersection over all ij such that si intersect sj is greater than k of getting ij. This is what we got. What we want is this. So how are we going to get that? So does this make sense? The analysis so far just showed that this is what it takes to get a single ij, but you want to get all of them. So how many samples are you going to need to get everything?
Well, the probability of not getting one of them is less than the sum of the probabilities of not getting one.
Okay, good. Exactly.
Maybe you need like n squared times delta, like log 1 over n squared times delta or something like that.
So what you need to do is, if you reset delta to be delta divided by n squared, then you'd be safe. Right? But then that's only going to, because you pay log in 1 over delta, you can afford to boost the confidence that much. Okay, so let me restate this. So let me, instead of delta over here, just to keep the let me say that this is what I want. So there's some beta and delta. I can get the probability of getting ij to be greater than 1 minus delta. What I want is actually some bound on getting everything. So flipping this around, the probability of not getting ij is at most delta. Okay. Now, by the union bound, the probability of the union over all ij si intersect sj greater than k of getting ij is at most the sum over all ij si intersect sj greater than k, the probability of getting, of not getting. This clearly is at most n squared times delta by the union bound. So we need to set delta to be beta divided by n squared. So this seems like you need a really tiny probability. But on the other hand, the cost in delta is merely logarithmic. It's only logarithmic. And so when you put it all together, what you get is O of the A transpose A 1 norm divided by K times log n plus log 1 over beta. This is what you need. And this guarantees that you get everything. So with the extra log n additive factor, you will get everything that is more than k. Now, this guarantees that we get everything at least k, but we might get small intersections. In an ML or in ML terminology or in I get good recall, but maybe precision is low. Maybe precision is low. Okay? But this is all I need. And if you wanted good recall and good precision, meaning you only wanted to report things that were large, to only output large intersections, to only output large intersections, all you need, if you put an extra epsilon square over there, then you can make it work. So what you do is you would do these many iterations and only report things that were seen often enough. So sorry, I just need to pause for just a minute. Okay, so to only output the large intersections, you have to modify the algorithm somewhat. So you're going to generate a bunch of samples and only take things that have appeared often enough. So this is not something, I will sort of leave that as an exercise that I will not talk about for now. We can discuss this maybe in a later lecture. But is this argument and is the algorithm clear? Any questions about this? Any questions? It's clear? So one of the things that I really want you to see is the power of the concentration and union bound, which we will sort of see over and over again in many other applications. And the point is, because the cost that you pay on delta is only log 1 over delta. So you can make delta go extremely large. I'm sorry, my apologies. You can make delta become extremely small at the cost of very few samples, and then with that you can afford to union bound. You can union bound over a large number of events. Any questions? Yes.
For the epsilon that we introduce later on, what are we approximating? What is our 1 plus epsilon?
So it's not okay. So let's say you wanted to output everything whose intersection is at least k, but you also wanted to output this is sort of poorly stated on my part. Let's say you wanted to output everything whose intersection is at least epsilon, and you do not want to output anything whose intersection was less than 1 minus epsilon times k. So I think I misspoke. You want to output everything whose intersection is at least k, and you do not want to output anything whose intersection is less than 1 minus epsilon times k. Then you would need that many samples. Right now, if you didn't have that, let's just say you just sampled and you just output everything that you saw. There are reasonable odds that you will actually sample things whose similarity, whose intersection is small simply because of the randomness of the sampling. In some applications, that's okay. As long as you find everything whose intersection is large, it's okay to also output things whose intersection is small, because maybe you'll filter them away through some other process. So often in many recommendation systems, this is okay, because all of this data that you get, like who are similar, is going to be fed to some machine learning pipeline that will take care of things itself. But in some applications, you actually only want to output things that are similar. So you want to output everything that's similar and only output things that are similar, in which case you need to do some more samples. The analysis then becomes more sort of Chernoff bound arguments. But I think that's somewhat of a, it's a good exercise, but will be somewhat of a distraction from the basic algorithm here.
Thank you.
Okay. Okay. So I still have about about 10 minutes. So I want to tell you about a really neat algorithm to sample from distributions, because this is something that that's been coming up a lot, and especially in this algorithm it came up quite prominently, which is how to sample from arbitrary distributions. So what's the setup? Given an array A of n elements, sample I proportional to A of I. Right? This is the setup. So I believe the question came up earlier. How do you represent a distribution? Well, I could represent a distribution, I should say, n numbers. Sample I proportional to A of I. Okay? So this is essentially the kind of question that pops up. Okay. Sorry, I just fixing something in the chat window. Okay. So let me give you the simplest.
When you say how to sample from an arbitrary distribution, you assume that we have the uniform distribution.
Good. Yeah. So good. So assume we can sample from the uniform distribution exactly. So you're given an array of n numbers. Let me think of this as just positive integers. Although you'll see that this really doesn't matter, but if that makes it easier for you to think, then you can do that. The simplest basic sampler, which is actually not all that bad, is construct the array B of partial sums. So B of I is going to be B of I is going to be assigned to all j less than equal to I of B of j. Okay, these are all the partial sums. So this is something like your CDF. I'm sorry? Yes, I'm sorry, A of j. That's right. All partial sums of A. Yes. So you construct the array of all partial sums, then sample a number, a uniform at random number in 0 to B of n to the sum of all entries, or B of whatever, B of n minus 1 or n. Let's just say I'm doing arrays, so I do n minus 1. Sample a number and binary search to output I proportional to A of I. Make sense? So what you did was, the one way to think of this is to represent things on the line. So let's just say again, all these numbers are positive, they're integers, so you start from 0. So this is going to be let me, let it, by for convenience, let b of 0 be 0. Okay, let me just sort of set this up so that b of 0 is 0. So let's just say a of 0 is 0, right? And then you have b of 1, b of 2, b of 3, so on and so forth, until you get to b of n minus 1, the sum of everything. And what you're doing is you just sort of say, I randomly sample something here, I randomly pick sample something here, and then I output 2. Or maybe I should output it's 1, 2, 3. I should output 3, right? So if I randomly sample something here, then this is assigned to 3, because this is exactly a of 3, this is a of 2, this is a of 1. I may have messed up my indexing there, so it should be less than equal to. And I should probably let this go all the way up to n. And this last thing is going to be a of n. Yeah. Or, right, so let me actually store my numbers going from a1 to an as opposed to a0 to an minus 1. But is this clear? So what is the preprocessing time? How much time does it take to preprocess? Given the array, how long does it take?
Length of the array.
O of n, right? N is the length of the array. What is the sample time? Log n. So to choose k samples, it's O of k log n. Right? So this is the basic sampler, which is actually not that bad. Let me give you, an improvement, a simple improvement. And the improvement is, if you want to choose k samples, now what you do is okay, so it's a sort of improvement. So choose, your k uniform at random numbers, because you need to choose k samples, right? Sort the k numbers, and then merge with b to generate the samples. So how long did it take to choose k samples? How long did it take? No, it didn't take k. It took more than k. What is it? You chose k uniform random numbers. You sorted the k numbers, and then you merged with. No. I meant the entire thing. The entire process to choose k samples, as in the samples from the distribution.
It's linear. Sorry. It takes k log k time to sort them.
Good.
Merging with b takes O of k time.
What is the length of b?
Oh, n.
N. So it's O of k log k plus n. So this looks kind of worse and kind of better. In practice, this is pretty darn good because these operations are extremely fast in terms of cache efficiency. So this is very cache efficient.
So to be clear, when you say merge, you mean a single step of merge sort?
A single step of merging sorted arrays, right? Merge sorted arrays. A single step of I don't know if I'd call it merge sort, but it's the merging operation. You have two sorted arrays, and then you merge them together to get the union of sorted arrays, or rather the sort of the union. Because k log k plus n, this is incredibly cache efficient. Even though this running time might be larger than that, binary search typically tends to be cache inefficient because there are lots of cache misses. This is often faster. But the best method, at least in terms of asymptotic efficiency, is something called Walker's alias method. This is a very, very cool procedure, and what you can get is a preprocessing, which is O of n, and the time per sample is actually just constants, O of 1. So you don't even need to do a binary search. So we have run out of time today.